Okay, so we're often worried about what's going on with indeterminate problems too. So like we saw with our axial stuff, we're going to need to have some sort of compatibility condition, and the compatibility condition that's going to be used is having the right angle of twist in order to make everything line up nicely. So in this instance, we have this A992 steel shaft. That's stainless steel. Has a diameter of 60 millimeters, fixed at both ends, and then at the at a point 1 meter from either side, we have a 500 Newton meter and a 200 Newton meter torque applied to it, both of those in the same direction. And then we want to figure out what sort of maximum shear stress actually occurs in this shaft. So looking at that, so again, I just redrawing our situation here. We're gonna and then we've got our free body diagram. So essentially, we're gonna have some sort of reaction at both ends. We're going to be assuming here that the force reactions are negligible, because they should be, because there's no force load. So all we're worried about is the torque going on. So we're going to have a reaction at A and a reaction at B. And I drew them on here in the opposite directions of the two loads because that's what it's obviously going to end up being. But the only equation we have here is basically to sum the moments about the x-axis is equal to 0. So we've got two unknowns in one equation. So we're kind of hooped if we try to rely upon just our equilibrium equations in order to figure out what's going on. So what we can do is we can use the principle of superpositioning. So basically, we kind of just treat it as if they were 3 bar or a single bar, the same bar, but we had 3 separate loads attached to it. So we'll apply, we'll remove the support at one end, and then basically we're going to have this the one with the first load attached, that's going to be rotating there, the one over here, and then a rod that has just the reaction at B applied to it. And then we know that basically the total twist when we add these up needs to be equal to 0 because this end here doesn't change position at all. So the total, basically we just need to we know what sort of twist happens when we apply it to when we apply torque over a length. I like to emphasize here that the twist only occurs over the length where there is some sort of internal torque load. So for example, here, where we've got the load applied here, we're going to get twisting going on here, but over here, there's going to be no twisting at all. No additional twisting, at least. I mean, this end, if we measure how much it's twisting, it's going to be rotating due to the load, but its twist is going to be exactly the same as the twist measured here, because the only actual twisting that occurs is due to this section here. This free portion here, that just rotates with this section. So same deal here. The length that we use for here would be this, and then obviously here the load, the torque is applied over the entire length. So yeah, so we're going to need to know what our J is. Obviously, we always need to know that. So pi over 2 times 30 millimeters to the fourth. gives us 1.272 times 10 to the 6 millimeters to the fourth. And then our GPA is just 75 gigapascals, again taken from the table at the back of Hibbler's with the material properties there. I'll be completely frank, I'm not entirely sure if your version of the textbook has that particular type of steel. For any of the assignments or quizzes from now on, I'm just going to be giving you the material properties as needed. But yeah, so we got the yeah, we just need to kind of add up the we need to figure out what the twist is for each of these scenarios. So for the twist for one, we got 500 Newton meters, and again I'm putting everything in terms of millimeters because we got this in terms of millimeters, so everything cancels out nicely. 500 Newton millimeters. 500 Newton meters times 1,000 millimeters per millimeters per meter times 1,000 millimeters. Again, it's a 1 meter section from here to here. Divided by our JG. I'm not going to tell you what those are. You can read it. Gives us 5.24 times 10 to the 3 radians. And then this scenario here, where we're twisting over this section, got 200 newtons, 200 Newton meters times the 2.5 meters. 2.5 divided by our JG gives us this value here. Same as that one. I'm not really too surprised that whoever designed that problem decided to make that the case. And then for scenario 3, our torque is the opposite. So again, both of these, based upon our sign convention, are going to be applying positive twists, because if we stick our thumb out in that direction, curl our fingers around, then it's going to be pointed in the same direction as the torque. Whereas for this one, in order to have our fingers curling around in the same direction as the torque, our thumb needs to be pointed in this direction. And it needs to be pointed in the negative x direction, therefore the torque and the twist that would be applied would be negative. So negative mb times the length there divided by our jg. That gives us this value here, so it'll be negative 3.76 times 10 to the negative 8 radians per Newton millimeter. This is what it kind of worked, what the units ended up canceling out to. Ended up with Newton left, and we ended up with on the millimeter to the fourth term. 2 of them canceled out for here, 1 of them canceled out here, so we ended up left with Newton millimeters down there. So we got that, and we just need to add those together. Those together need to be equal to 0, because we know that when we look at the end here, the end there needs to have no rotation relative to here because it is fixed. They're both fixed, so the end you can have rotation in the middle. You absolutely can and will have rotation in the middle, but you can't have any at the end, at the 2 fixed ends. So anyways, we are going to be able to solve for what our MB is based upon that. And that'll be that'll give us 285.6 Newton meters. So if we got that, we can just sum up our mx so sum up the moments. Those need to be equal to 0 to find out what a reaction at MA is. So minus MA plus the 500 plus the 200 minus this gives us an MA of 414.5. Sorry, 414.4. So here's just a redraw of our three-body diagram with those things on there. And then I'm going to plot the torque as a function of x in Newton meters. So again, if we look at a little section right here, we're going to have torque going that way, and we're going to have the counteracting torque going that way. So again, if we stick our thumb out in this direction, our fingers are going to be pulling around this end. So that means that that's going to be a positive 414 Newton meters that we need to apply. Then again, and then we hit the 500 here, and that drops us down to negative 85.6. And then we hit the 200 there, and that drops us down to negative 285.6. And then, of course, we hit the end here, and that brings us back up to 0. The value. It's always helpful when the value that we end up at the end allows us to cancel out when our final reaction is applied. It means that we didn't screw up, or at least it means we didn't screw up in a really obvious manner. So, absolute value of our torque is going to be 414.4 Newton meters. So we can, based upon that, we can calculate our, the largest absolute value of our torque is that. So based upon that, we can figure out what the maximum stress level that we're going to be seeing is. So that'll be T times the radius divided by J. So just plugging those values in here allows us to solve for our tau max. Our largest shear stress is 9.77 megapascals. And yeah, that's that.